Hello and welcome to this fourth video for sections 3.1 and 3.2 of calculus class. I'm going to talk about one-sided derivatives and a little bit about the alternate definition of derivative, and the big important part here is this more notation section, because we do want you to know the different ways the derivative can be written and asked for. That becomes important. Different books use different styles. There's Newton's notation, there's Leibniz's notation, and there's several others. So we don't want you to be confused by the symbols. One-sided derivatives is not going to be fundamentally important to what you do in this section of the text of the course, but it is related to what we just finished in limits. So we had the idea of continuity in the last section, or in the end of the last unit. Continuity, meaning the function can be drawn without lifting your pencil from the paper in the most simple, concept, if you think of it that way. But there's no holes or vertical asymptotes or jumps in the graph from x equals a to x equals b. That's what this interval means. It would be continuous. Differentiable means it has a derivative everywhere from x equals a to x equals b. Well, it turns out you don't have a derivative at any point where you don't have continuity, because what the derivative is really, you can look at the derivative like this. This would be the right-hand derivative. If you make the space between your points become really small, and you make that just a little bit on the positive really small, so the delta x is a slightly positive but very, very tiny number. And you have a function, there's your there's your x plus h, there's your x, and this is very tiny. You're coming at it from this way. That would be the right-hand derivative. Now, if the function is continuous, the right-hand derivative and the left-hand derivative would be the same. But what happens is if you had a function that changed, went like that, and then suddenly jumped down, the derivative in this function might be totally different. Might be a step here, might be a parabola there. You might have different right-hand and left-hand limits, in which case, at this point of the jump, and this is not drawn very well, admittedly, you would not have a derivative. The bottom line is if you have a point of discontinuity, if you see you have a step discontinuity, or you have a place where you have a hole, here, you've got that. It turns out the limit doesn't exist here, so it turns out you don't have a derivative there. You have to be continuous to have a derivative. The right-hand derivative would be the slope coming from the right. So take the absolute value function. The slope coming from the right, this is the absolute value of x, is going to be positive 1. The slope coming from the left as x goes to 0 is going to be negative 1. So what you say is the slope at 1, these things don't match, so I don't have a slope at 1. I have a sharp point. So besides places we have discontinuities not having derivatives, you don't have derivatives at sharp points. We're going to see that again in another video in this section too. But that's the idea of a left-hand derivative and a right-hand derivative. The best example is this absolute value function. This is just a piece of a line with a slope 1. So as you go to 0, the left-hand derivative is different than the right-hand derivative. That's an unusual situation. But it turns out that for the derivative to exist, the left-hand derivative and the right-hand derivative have to match. So we say a function is not differentiable at a sharp point, because if you have a cusp, even like that, that's another way this could happen. We'll look at some curves like this later. This is a sharp point. You have a positive slope and then a negative slope suddenly. Sharp positive, then sharp negative, doesn't match. If you have a function that goes like this, we see this a lot in algebra-based physics. This piece of a line, then this piece of a line. The function's continuous there, but that's a sharp, sudden change. This slope would be 0, and the slope would be positive. Say it's positive 2. What is it at this point? You don't know, because there's a sudden change. That's the idea of a one-sided derivative. I won't be making you calculate a lot of those, but I do want you to have the idea. That's why you don't have a derivative at a sharp point. It's because the derivative suddenly the derivative on as you approach from the left and as you approach from the right is not the same. Remember, derivative fundamentally is a limit process. If the left-hand limit and a right-hand limit don't match, you don't have a limit. So if a left-hand derivative and a right-hand side derivative don't match, you don't have a derivative. Let's take a look at some more notation. So the derivative is a slope. Slope. The big idea of slope comes from this notation. Change in y over change in x. You learned that a long time ago. Don't join the upside down slope club and do change in x over change in y. People do that a lot in algebra courses. Harder to do in calculus, though, because our slopes are from functions. Y prime, a single quote. If you put a double quote, it's the second derivative. You put 3 quotes, it's the third derivative. You can keep taking derivatives. You can. The second derivative is just the derivative of the first derivative. df dx, the derivative of the function with respect to x. What it comes down to, and if you look at this bottom one, is this is what we call an operator. It means take the derivative of what follows, and x is your variable. Okay, the significance of the x is it tells you which letter is varying. So that's what you take the derivative, and this becomes important in the chain rule, with respect to x. That's the importance of that notation. Sorry for my handwriting. I am trying to get these done quickly because somebody pointed out they were missing. Okay, so that's your notation. And there's multiple ways we can write it. You'll see probably mostly this and this, but you will start seeing more of this as you go on in mathematics. The derivative as an operator. So because it's an operator, if you have an equation and you take the derivative with respect to x of both sides, you still have the two sides are equal when you're done. It's an operator like adding or subtracting in some ways. All right, let's go down to the next topic here before I end this video and start a new one. So this is the alternative definition of a derivative, and it's useful when we look at continuity, but we're going to be using this as our definition of derivative going forward. The limit as h goes to 0 of f of x plus, sorry, I didn't do that right, f of x plus h. Let me pull up my eraser and do that right. Instead of doing it fast, let me do it right. Let's see. F of x plus h minus f of x. And you've been doing this. You've been doing this whole, even you had numbers sometimes instead of x. You had to find the function at 2 plus h minus f of 2 over h. Well, in that case, if you have a function and you have 2 points close together, and they'd be a lot closer together than this one would be x, and this one would be x plus h. And the heights are f of x and f of x plus h. In this definition of the derivative at a particular point, this should be f prime of x, first of all. F prime of x equals the limit as x approaches c. Well, that's saying the same thing. As h goes to 0, these 2 points get really close together. So f of x minus f of c over x minus c, that's slope, change in y's over change in x's. Don't be upside down on that. So instead of saying this is f of x, instead of saying this point is x, we're saying this point is c and its height is f of c. That's all. What you're saying is those two numbers get closer together, you get the derivative. We will be working mostly with this definition of the derivative, though, but I just want to show you it's just a different way of noting the same concept. Okay, so I'm going to stop this video right now, and I will see you in the next one. And thanks for joining.